This lesson is on peak versus RMS voltage and current. Peak is like the maximum, and RMS is another word for average. Um, in our Unit 8 overview sheet, in our third objective, we have already completed the first one, and we are going to only do the second one today. Solve problems involving the average power in an AC circuit. So due to the nature of alternating current, where we have an alternating voltage and current, the average is kind of hard to calculate, so we're going to show you the way to do that. So in this warm-up, a coil rotates inside a uniform magnetic field with the magnetic flux graph shown. Draw the corresponding EMF graph. So go ahead and pause it right now, and I will return with the graph. So in my magnetic flux graph, I've identified where I have zero slopes, maximum positive slopes, and maximum negative slopes, and recognizing that the slope is proportional to the EMF, and so rather the negative slope is proportional to the EMF. So I know where my zeros are, so I know that's where it crosses the x-axis, and then I know when I see the blue positive first, right here, it's going to be a maximum negative due to the negative in the equation. So I should end up with a graph that kind of looks like this. So it's a sine graph that turns into a negative cosine graph. All right, so one thing to recognize, and I kind of already said this EMF is alternating, so we have to try to find out how much power we can extract from an alternating power supply. So if we were to look at this and we say, well, what is the average? And you might be able to say, okay, there's positive here, and it's in the negative here, and they're both equal, so maybe this is zero. Maybe the average is zero, and that is wrong. That is not what it could be, because as it alternates between zero and peak voltage, the only moments in time in which no power is transferred is like at the zeros. But whether it's moving forward or backwards, you are still exchanging the kinetic energy of the electrons to some energy wherever it's traveling to, as it oscillates between what we call the peak voltage. So V naught is what we're going to call peak voltage. And similarly, I naught is going to be peak current, which is pretty much just maximum. So we need to find a way to calculate the average voltage applied, and therefore the average current. And using that, we're going to find this average power. But average is a little hard to do. So what we're going to do is we're going to do the RMS, which stands for root mean square. So first, we're going to square this graph. And once it's squared, it's all positive. So first we square it, right? So we see we're squared. And then we take the mean. So root mean square, right, is... So we kind of actually read it from right to left. So first we take the V and we square it. Then we take the mean of that value. And then we want to get back to our like unsquared version. So we take the square root. And then that'll give us our root mean square of our voltage. And that is what we call, in quotes, an average. But it's not technically an average because it's kind of a, it's like a statistical calculation. So that's why we call it root mean square voltage, or RMS voltage, or VRMS. So with that, we can look at our RMS for our voltage, our root mean square for our current, and then our average power, which actually doesn't come from some root mean square. It comes from the values, the, in quotes, average values of voltage and current. So our peak values are V naught, I naught, and then power, it's not really a peak power. They write it like this, P max. So to find our root mean square for our voltage, we showed that work over here as we go squared it, meaned it, and then rooted it. So we should end up with V squared over 2. But because we're looking at the root mean square, we actually want to square the maximum, because that's going to be kind of our, right, that's the mean value that we see in the graph. So actually this should all have our maximums to get to that mean value right here. So that is just V naught over square root of 2. And that's equal to our VRMS. Similarly, our IRMS, the RMS value for our current, is the same, just with our current peak current value. And now for our RMS value for power. Well, we don't really use the term RMS for power. We just say P average. So we can write it two ways: P average, or you're going to also see it as P bar. And that's just another way of writing like the mean of the power, which is the average. So to solve for that, right, which let's just call it P bar because that's what it says in your data booklet. That's just equal to the IRMS times your VRMS. And so I'm gonna, if I plug my values in, I get I naught over square root of 2 times V naught over square root of 2. Let's make that smaller. And that just becomes I naught times V naught over 2. And that's your average power. Now, obviously, you can also say, oh, okay, duh. You know, that's half of my maximum power. That's my average power because of the way we use the root mean square. So that's that. One thing I didn't write is P max is just I naught V naught. Like kind of the same equations we've done before. These equations are in your data booklet. All are in data booklet. So now that we have these equations and we've looked at the values and seen them as averages, we want to actually say, why do we need these values? Like, why can't we just use this peak value, this peak current? Why do we need average values? And it's because before we had alternating current, we had direct current. And if we want to use alternating current to match the levels that we have in direct current, we need to find how much power we can extract from an alternating power supply. So these RMS values, the definition really means, right? Let's look at this right here. The RMS or average voltage is defined as the value equivalent of the voltage if it were a DC circuit with the same resistance. So if you put two circuits side by side, one's AC and one's DC, in order for those to produce the same power output in a circuit, the RMS value for voltage and current must equal the direct voltage and current values. So that's our connection, and that's why we do it. So RMS voltage in an AC circuit is equal to the constant voltage in a DC circuit. All right, let's do some practice. We have a graph. This graph shows the variation with time t of the output voltage V of an AC generator of negligible internal resistance. A resistor of resistance 25 ohms is connected across the output of the generator. Calculate the RMS value of the current in the resistor. So first we need to identify our maximum voltage, which is 100 volts. And we want to somehow get to a RMS value of current. Something to note on the side is that R is equal to V naught over I naught, or R is equal to V RMS over I RMS. And this is said in your data booklet as well. It's kind of obvious, but it's there just in case. So I know that when I'm using a resistor, the resistance value, that doesn't change depending on AC or DC. But I want to make sure that if I'm using my peak values, I stick with my peak voltage and current. My RMS values are my voltage and my current. So do not change. Let's make that R better. Yeah. So I may want to find my there's my RMS value for voltage, but I could also find my peak current value and go that direction. But I'm going to find my RMS value for voltage. So my V RMS is equal to V naught over square root of 2. And so that's going to be equal to 100 over square root of 2. And that's equal to 70.7 volts. All right, so I have my RMS value for voltage. I need to find my RMS value for current, and I know my resistance. So just what I noted over here, right on this side. I'm going to stick to my RMS value for voltage to find my RMS value for current. So my I RMS times my R, right, is equal to my V RMS. So I can, this is just V equals IR. And so I can find I RMS by dividing R both sides. And I get I RMS is equal to my V RMS, so 70.7 divided by 25. And that gives me an I RMS of 2.83 amps. So I've got my I RMS and I've got my V RMS. And I've answered the first question. The second question is calculate the average power dissipated in the resistor. Well, we know the voltage, the RMS value for voltage across the resistor. We know the RMS value for current across the resistor. So we know how to find this average power, P bar. That's just right, P average. And that's equal to 70.7 times 2.83. And that gives you 200 volts. How did it end up getting such a perfect number? I want you to think about this and see if there's another path you can take to get to 200. And I will pause it and do it really quick and show you. So if you want to think about it, pause this video to think. So we would have to find our maximum current and then find our maximum power and then divide that by 2. So 400 divided by 2, that's 200 volts. Either way, you can get to the same path. All right, well, I've got one more question. I mean, I want to eventually kind of solve for all this, but I've almost done it. So let's do this part 3. Calculate the power dissipated in the resistor at 0.4 milliseconds. Now, since our voltage is alternating, our current is also alternating, so our power is also alternating. So what we found is a peak power and an average power, but we can also find this instantaneous power using the graph. So I know that at 0.4 seconds, I have about, looks like 60 volts. I want you to solve this problem. Pause this video, solve this problem, and I'm going to work it out as well. So instantaneous power occurs with instantaneous voltage and instantaneous current, so you don't really have to worry about RMS in this case because we're not looking at averages. So we have a 60 volts. I can find my current using I is equal to V over R to get 2.4 amps, and then I just do P equals IV. So that gives me 144 watts. Great, let's just fill all this in just to make sure we got it, right? V max, which is 100, it's V naught. I naught, we already found to be 4 amps. V RMS is 70.7 volts. I RMS is 2.83 amps, and our average power is 200 volts. So we've already solved for everything there. So to kind of combine everything, we know that the changing magnetic flux produces a changing or alternating voltage and current. That alternating voltage and current, we want to relate it to the power supplied from a DC power supply. So we need to find some average value, which average is kind of hard. So we find an RMS value, which is the squared, the root of the mean of the square of the voltage. So we square the voltage, then we mean it, divided by 2, and then we take the square root of it, and that gets us back to some version of an average. And we can do that for voltage and current to help us find the power, and it ends up working out where the average power is just half of the total power. That makes sense because it's alternating, so it's just going up, down, up, down, up, down. And then we've solved the problem using this pattern. And really the most important conceptual understanding is this definition that it's the value equivalent if it were set up right next to a DC power supply. So we know how much RMS value we need if we know how much DC power it required as well. And that sums it up. I will give you the practice problem. See you in class.